So let's get started. Any course that is concerned with the fundamentals of electrical engineering has to be concerned with information. And that's what we're going to talk about today to get started. So it turns out what's really going to be important for us are signals and systems. So the first thing I'm going to do is define a signal. It turns out this definition is very simple. You already know what a signal is, it turns out, and we'll get through that very quickly. What's going to be more important are the various kinds of signals, how electrical engineers think about signals, the different ways in which we think about and categorize them. And then I'm finally going to link information to signals. And it turns out this link may be a little bit tighter than you think. I'm going to say some provocative things, I hope. Finally, we'll talk about systems, which are the way you operate on signals. And we're going to put systems together to create what is known as the fundamental model of communication. This model is very, very important. We're going to return to it throughout this course because not only will, in the process of understanding it, will we understand how real communication systems work, but we'll also, when we put the various components together, we'll be able to apply the things that we learn in this course. So what's a signal? So the definition of a signal is quite easy. It's a function. So anything you've learned about functions in calculus, you've already learned about signals. They're exactly the same thing. There's no difference. So I can plot a signal. So let's say we have a signal as a function of t, which I take to be time, and I'm going to call my signal s of t, and there it is. That's a signal. That's all there is to it. There's nothing more complicated about a signal than that. It's just a function. And before we get too far, I want to talk about electrical signals. And there's some interesting aspects of electrical signals that have proven to be very important in the information age. As you know, electrical signals are voltages and currents and electromagnetic waves. What's very important to appreciate is that they carry two different quantities. First of all, they carry power. When you plug into the socket in the wall, that's an electrical signal that's carrying power, which powers your computer, your refrigerator in the home, the laser printer in the office, all kinds of things. Very important. There's also signals that convey information. For example, the wireless signal that you use with your cell phone to call one person is carrying information, is carrying what you're saying. Now, it turns out we're not going to talk much about power in this course. It's not our major concern. What is our concern, of course, is information. But you cannot design an information system without having some consideration about the power. How much power am I using to call somebody over my cell phone? How efficiently am I expending that power? These are going to be issues that are very important to the design of modern information systems. So we've got to talk about power a little bit, but we won't certainly focus on it. It will come up. So the various categories of signals, how do we think about them? Well, there's two broad categories, analog and digital. An analog signal is a function of a continuous variable. So here's my good old s of t again, and it's a function of time. And certainly time is a continuous variable, and we can plot it. Looks something like that, very crudely. The sinusoid, the sine wave, is governed by three parameters. First is the amplitude, which determines how big the signal is. The frequency, f0, determines how often the peaks occur. If I were to whistle, that turns out to be an acoustic sine wave, at least approximately. The frequency of my whistle, the pitch of my whistle, corresponds to the frequency f0. Phase has to do with how the sine wave begins at the origin. So here we have a very good analog signal. It's a sine wave, has an explicit formula controlled by three different parameters. Now the next analog signal I want to talk about, though, is a little different, and it's different in a very interesting way. So here's a plot of a segment of speech. That's me saying the vowel E, and what I want to point out is that there's no formula. The sine wave has a formula. There is no explicit analytic formula for speech. However, we are going to want to operate on signals to understand the structure of signals, whether there's a formula or not. The structure of the signal with a formula, like I said, is governed by 3 parameters. Here, we're going to have to think about what, and for the speech signal, what the structure of it is. It kind of looks like a sine wave, but I think you can see that the succeeding peak values don't look the same. The peaks of these waveforms don't look the same. However, the peaks of every other thing tend to look the same. This is even more apparent at the bottom, where there's the big guys, very negative peaks, and then the ones that are smaller, less negative, and they kind of interlace with each other. Well, that's a very tedious way to try to get at the structure of this signal. We're going to develop much more interesting ways and much more informative ways to appreciate the structure of a signal. But we will have signals that don't have any formula. We'll have signals that do have formulas, and we have to develop methods by which we can appreciate the structure and process these signals, whether or not there is a formula. It's going to be very interesting for us. So the next kind of signal is a digital signal. And a digital signal is a function of the integers. It's a function of a discrete valued independent variable, which we're just going to take to be the integers. So here's an example of a digital signal. It's a sequence of numbers. So I intend for these numbers to be read from left to right, and here's a plot of it, just for fun. So this goes across like that, and that corresponds to the sequence of values that we see across here. So from left to right to top to bottom, you see the values of my digital signal. I don't mean you, but I don't see much structure there. I don't quite see what's so interesting about this signal. I do want to point out before we get too far along about how I plotted it. This is what's known as a stem plot. And every value is drawn with a little line, with a little bubble at the top to indicate the value. So this indicates that this function only exists at the integers. The value at 29.5 doesn't exist. It's not even defined. This is a function only of the integers. That's what a digital signal is. So, what is this thing? Well, it turns out this is another digital signal. This is text. And you may say that's a signal. Well, it turns out if you take position of the character along the line, the value of the signal is a member of the alphabet. So S of 1 is capital T. Well, that's a digital signal. It's a function of the integers. What's even more interesting about this example is that these two are the same thing. So I typed this text into my computer. Inside the computer, what the computer did was turn those symbols, the typed characters, into numbers. So a capital T is 84. A lowercase h is 104, etc. So they're exactly the same. So I think you'll agree that the text version, you can understand the structure. You know, it's English text, for example. It's not something random. It actually makes sense. Whereas if you look at it as a sequence of numbers, it's not quite apparent. And certainly if you plot it, it's even less apparent what the structure is. The structure of a signal may depend on how it's presented. I find it kind of interesting thing to think about. So let's talk about some other kinds of signals, another way of categorizing them. And I want to talk first about images. So the speech signal we already talked about is a function of time. Images are functions of space, so they're a function of x and y. So I can give you an example of a black and white image. Here's a picture of a woman. And you may say, why are you showing a picture of a beautiful woman? Well, it turns out this image has been used in the image processing field for decades as a test image. And here's why. This one image contains a curve, contains some straight lines, contains a corner, contains a highly complicated area, something we call texture, contains a smooth surface with a gradient of shading, and it certainly contains a face, a very important thing. So if you're trying to develop an image algorithm or image processing procedure, you want an image to test out how well it works. Well, you may discover that your procedure works very well on straight lines and curves, but doesn't work too well on texture. And so you want an image to test it with. Rather than having a textured image and a straight line image, etc., it's a bit more convenient just to have one image you can run through and see how well it works on that. That's why electrical engineers develop such test images. So this one has been used for decades because it has all the right things in it that you need to test out images. But is it a function? Well, I'm going to plot it. So here it is as a function. So here is the x and y, and this is what's known as a heat map. This is a way of plotting what we call two-dimensional signals, so that you can readily see what's big and what's small. So big values are indicated in red, and big in the image turns out corresponds to white, so it turns out that corresponds to that little area right there. Blue values are small, and that corresponds to black. So the grayscale values in between are somewhere in between. This is called a heat map because the big values are hot, they're red. The small values are cold, they're black. So this is just a very convenient way of looking at a plot of such a signal. However, here we have the same situation we just had with the digital signal. Looking at the image, the plot of the function, I have a hard time appreciating what it really is. It's a lot easier for me as a human to look at the image as opposed to a plot of it. But again, this is how the computer sees it. There's absolutely no difference between the two, and we are going to develop more insight into the presentation of information as we go through the course. Now, another kind of signal that's interesting is video. As you know, video is a sequence of images occurring in time, so that makes it a function of three variables. So, space and time. So, the jargon is that an image is a 2D signal because it depends on two variables. This is a 3D signal because it depends on three variables. And this is common terminology. So, again, a one-dimensional signal was, for example, speech, what we saw earlier. But it can be a little bit more complicated than that, because if it's color video, it actually is three 3D signals rolled up into one, considered as a signal. So our color video actually consists of a red, a green, and a blue signal, each of which is a function of space and time. So this is a multi-valued signal. So this image up here is in color as an image, not as a plot, but as an image. And it's still considered a 2D image. So again, the dimension of a signal has to do with the number of variables upon which it depends, not how many values it may have. So this 2D image here has red, green, and blue components, each of which is a 2D signal. Now let's bring in information. Where's the information? So I'm going to say something controversial here, that information does not exist without a signal to represent it. So let's think about this for a second. I've already shown you that text is a signal. So all books contain signals from one viewpoint. Certainly there's more to it than just that. It's the structure of that signal that conveys information. You may say, well, information exists without there being a signal. For example, a memory that I have in my head. Well, it turns out that memory is mediated and brought to fore in your brain by electrical signals. And we'll talk about that a little bit. So there is no such thing, information just existing in and of itself without there being a signal to represent it. So signals and information are linked together in very important ways. Not all signals contain information, but information doesn't exist without there being a signal alone. So we talk about information being encoded in a signal by modifying its structure. That's why I was talking earlier about the structure of a signal, because that's where the information is. It varies the structure of the signal. That's how you think about it. So what we're going to do is look at this sine wave. So if I take this signal, which we've already talked about, has 3 parameters highlighted in blue here. If I change the amplitude of that signal in such a way that the amplitude varies according to the speech signal that I'm producing now, that turns out to be what's called amplitude modulation, and that underlies AM radio. If I change the frequency according to what I say, that gives you frequency modulation, or FM radio. There is something called phase modulation, but it turns out it's not used very often because it's been shown that frequency modulation has better technical characteristics than phase modulation. But anyway, that's why I wanted to find out what the structural components of a sine wave were, so that I can change those components according to the information I want to encode in. So what does a system do? Well, it's a system that operates on signals to produce a modified signal. So the system might do the encoding of information, and it also can do the extraction. It can also is the thing that extracts information. Now the way we indicate systems is with what's called a block diagram kind of thing. So here's the idea. The input to my system is X. It's always, in most drawings, comes in from the left side of this block box that denotes the system. The output is Y, usually comes out from the right. And so the arrow indicates the inputs, and the arrow coming out indicates the output. So what this system does is it operates on the signal X, does something, who knows what, and produces an output Y. So we could go down the mathematical path to talk about functions that are functions of functions. So that path turns out to be overly complicated. We won't need to go down that path. We'll just learn and talk about systems as things that take as an input a signal and produce another signal. So here's that fundamental model of communication that I was saying earlier is so important. It's a sequence of systems. I've labeled important signals. The source, the idea is there's a source that has a message signal. And the goal of a communication system is to get that signal over to its destination, which technically is called the sink. I do not know where the term sink comes from. It's just the terminology it's used. We'll just go with the flow and use that terminology. But the idea of communication is to get something that contains information from one place to another. Now it turns out that'd be easy if it wasn't for this funky cloud-like thing in the middle, the channel. That's another system, but I've drawn it like this because this basically refers to phenomena we have no control over. And let me guarantee you that the channel, nothing good happens to a signal in a channel. What comes in is not what comes out at all. In fact, the channel can do things to signals that you may not know in great detail. So, trying to send the message M directly through this channel is a big mistake. In most cases, it won't get through. So here's what we do. We're going to take our message signal M and put it into a transmitter. And what the transmitter does is creates a signal which is better suited to go through the channel than the message M would be. This is called engineering design. This is what electrical engineers and communication engineers do. Try to get signals through the channel. So this is termed the modulated message. That's what a transmitted signal is. Transmitter is a box which takes the message M as an input and produces X as an output. That goes through the channel where nothing good happens and produces the received signal R, which is, trust me, is a corrupted modulated message. It's going to do all kinds of things. Nothing good happens in a channel. The receiver's job is to try to figure out what that message was that was being transmitted, despite the fact it's been corrupted. So I put this hat on top of the symbol here because it means that it's not exactly equal to M. So it's an approximation to M. So M hat basically equals the message M plus some error. And one of the things you want to do when you design communication systems is to try to fight the channel so that you can minimize that error. And it's this message M hat that goes into the sink, goes to the destination. That's what you get. It's known as the demodulated message. So here are all the labeled pieces of our fundamental model. We're going to talk about this again and again. We're going to worry about how transmitters are designed, how receivers are designed. Turns out you cannot design these without designing them together. And we will talk about that as we go through the course. So this is the fundamental model. You now know what a signal is, you know what a system is generically, and now we're ready to get serious and talk about things together.